The masses of stars in a binary system are found by using Kepler's third law. We thus need to measure the orbital period p and the separation distance a between the stars. Using this law, we get the combined mass of both stars. Then, by comparing the distances of each star to the center of mass point between them, or by comparing the speeds of each star around the center of mass point, we can determine how much of the total mass belongs to each individual star. Recall that the more massive the star, the less its speed around the center of mass point. For example, if a star is moving with an average speed that is only 1/4 the speed of its companion, or if that star is found to be only 1/4 the distance to the center of mass point than its companion, then that star has 4 times the mass of its companion. If stars in a binary system have sufficient angular separation so that both can be seen as separate stars, they are called visual binaries. By measuring the distance to the system, and by watching the motion of the stars over time, we can determine their separation distance, orbital period and the location of the center of mass point. From this we can calculate the mass of each star. Usually, the angular separation of the stars making up a binary system is so small that all we see is a single speck of light. If repeated observations are made, then absorption lines from the two stars will do a kind of scissors motion in the spectrum, as shown. The maximum shift of absorption lines from each star can be used to calculate the speed of the star from which that line comes. The period of time from maximum redshift to the next maximum redshift is the orbital period of the stars. The orbital period is obviously the same for each star. Data about the speeds of the stars at different times can be used to plot what is called a velocity curve. Recall that it is the radial velocity that is measured using the Doppler shift. The orbital period is the time between successive peaks. Note that it can be seen graphically that the period is the same for each star. The velocity of each star, which is the peak of the radial velocity for each star, can be read off the vertical axis, as shown. In this example, the period is 4 years since there are 4 years between peaks, 5 minus 1. The velocity of the faster star is 50 km per second and the velocity for the slower star is 40 km per second. If we assume, for simplicity, that the orbit of each star is circular, then we can easily see how their speeds and period can be used to calculate the separation distance between the stars. The distance of each star to the center of mass point is equal to the circumference of its orbit divided by 2 pi. The circumference of a star's orbit is its average speed times the orbital period. Once the distance of each star to the center of mass point is calculated, then they can simply be added together to get the total separation distance a between the stars. This is the distance that is needed to plug into Kepler's third law. Once we have calculated the separation distance, we use that along with the orbital period to calculate the total mass. Using the velocity ratios, we can work out how much of that total mass belongs to each star. For example, if we have a total mass of 6 solar mass units, and one star is moving at twice the speed as its companion star, then that companion star has twice the mass. The companion star must have a mass of 4 solar mass units and the first star 2 solar mass units. Doing the math, if x is the mass of the first star, then the companion has mass 2x. We know that x plus 2x equals 3x equals 6, then x must be 2. The first star has mass of 2 solar mass units and the companion has mass 2 times 2 or 4 solar mass units. As always, because the Doppler shift only reveals the speed of motion directly toward or away from the observer, then if the system is inclined by an angle other than 90 degrees, the entire velocities of the stars will not be measured. This issue was also encountered in a discussion on exoplanets. If the inclination is not known, and it often isn't, then the masses calculated are only lower limits. All we can say is that these stars have at least this much mass, but we cannot be certain of the actual masses unless the inclination is known. If the binary system is such that the stars periodically eclipse each other by passing in front of one another, then we know the inclination angle is indeed 90 degrees and that any masses found by using Doppler data are the actual masses. Eclipsing binary systems are identified by their light curves. When one star is passing in front of its companion, it's blocking the light from the companion and thus the system momentarily drops in overall brightness. The drop in brightness is greatest when the dimmer star passes in front of the brighter star. The complete masses of many such eclipsing binary systems have been determined.